Here it is. All right, good morning. So we are going to start off with doing a synthesis problem that we had written on the board at the end of yesterday. Let's see if I can find it. There it is. Okay. There was a question in the chat. So the first exam will start it'll start at 9:15, which is our normal class time. And then, yes, we'll take the exam via Zoom. So it'll be a PDF. You guys will print it out, fill it in, and then scan it and upload it. And you'll have the entire class period. We will not have Resi the days that we have exams. So I think the first one is on a Tuesday when we don't normally have a Resi, but then the next two are days when we would. So we won't have a double dip on those days. Okay, so if you look at the practice or the previous exams, it's going to be almost identical except for just different questions. So yes, you want to be somewhere with a printer. I'll make an announcement about it today as to what exactly you should have, but yes, I would be around somewhere with a printer. Okay, so can we take photos to upload instead of scanning? Yeah, I mean, I think most people use like Scan Genius or something on their phone to upload it. So yeah, you can take photos. If you don't have a printer, I'll have you email me and we'll figure something out. You can also use like an iPad or something like that if that works better. All right. Let's get started. So taking a look at this synthesis problem here, we have one less carbon in this skeleton here than we do our product. If you want to count these out, We're clearly missing a carbon on this chain here. So in order to add another carbon, we're going to need to make an alkyne. So in order to do so, we're going to have to go through kind of our elimination pathway. So adding in a base is going to make an alkene. From here, we could add in. So going from an alkene to an alkyne, as we talked about, is kind of uses the same technique every time. So adding in something like Br2. Followed by excess base. Will let us make this into a triple bond. So as we mentioned, we were one carbon short here. So in order to elongate this by a carbon, we're going to have to add in our base and the NH2 followed by some sort of one carbon elongator. So I like to use methyl iodide. And then from this point, we want to have trans chlorines. So we can just add in Cl2 to get to our final product. How many steps is this? This is 1, 2, 3, 4, 5 steps. Any questions on this synthesis? Okay, so today we're going to talk about NMR. If you go into the modules under module 1, there is a worksheet that I'm going to be working off of. So, all right, we are dealing with, in this class, we are going to specialize in what's called proton NMR or H1 NMR. And essentially, what this is we're looking at the protons on a molecule. So if we have a molecule like this here, each one of these proton sets are going to give us a signal. There's the same symmetry we've been kind of talking about previously. So this here would end up giving us giving us one signal for these two positions because they're symmetrical. if we have something that has no protons on it, for instance, this here now, where we would still get a signal here, here, these would be grouped together. This carbon, which has no protons on it, is not going to give us any signal because we're dealing with proton NMR and we're looking to recognize just that, protons. So let's talk a little bit about what we're actually looking at when we look at an NMR. We got a couple of different factors. So one thing is you'll always get a formula. So right here, you can see that this is C3H7Br. And that's going to tell us a good amount of information. There's a couple of things that we want to look at immediately. The first one is going to be our integration. So the integration is going to be this number with an H next to it. You can see a couple of them down here. Typically speaking, this refers to, if we're doing an all carbon example, this would be like a CH, another CH here. This would be a CH3, CH2, CH3. 6H generally speaking refers to as two symmetrical CH3s. Probably something like this. So that's what our integration is. Ooh, can I erase just some of this? After we look at the integration, we want to look at the number of peaks on the signal. So for instance, let's take a look at this 6H here. This has two different peaks on it. This is referred to as a doublet. And what the number of peaks tells us is our number of neighboring hydrogens. Minus 1. So usually the way I like to do these is I'll write out the peak number. So this has two peaks, and I'm going to put a 1 underneath it to signify this has one neighbor. This one over here, it's a little bit difficult to count, but there's 1, 2, 3, 4, 5, 6, 7 peaks. So we would write a 7 here with a 6 underneath it. On an exam, I would give you the number. I would write like, do a little 7 peak kind of a thing, so you guys don't have to try to figure out really small signals. Okay, so what does that mean? Number of neighboring hydrogens. So let's take this example again. we're going to focus on this center here. So if we had a peak for this center, which when we actually start doing these NMRs, will be a little bit easier to see. The number of neighboring hydrogens to this center is going to be these on the left, and then this one here on the right. So this would have a total of 4 neighbors. Which means it should have 5 peaks. If we're looking at the NMR, we would see 5 peaks and know that it has 4 neighbors to it.
Excuse me, why is the other 2 hydrogen on the right are not counted as well, only one of them?
Why are the other ones not counted?
Yeah.
Yeah, so it's your neighbors. It's going to be not like, it's 1 away, not more than that. So if we had a long chain, and we're looking at this position, when we're dealing with its neighboring hydrogens, that's only going to be these ones. And then similarly, if we were looking at this position, its neighbors would just be these ones in black. You're just looking at 1 position away. So we don't count these hydrogens because they're 2 carbons away from the center. Okay. The last thing that we need to look at is going to be the shift. And this is going to tell us if there's anything large attached to our molecule. And I'm going to go over shifts the more that we do them. So generally speaking, carbon by itself, like long carbon chains, are always going to show up in this, like, let's say 0 to 2 range. Typically it's around 0.5 to 2. This is the range that just carbon by itself shows up. Once we start bonding to electronegative molecules, like for instance, we know we have a bromine in this compound here, that's going to shift it in this ppm range further to the left. So generally speaking, if you have a bond to a halogen, let's say there's a Br on this molecule, it's going to change the position of this H from being in that 1 to 2 range. It's going to shift it all the way down to kind of the 3 to 4 range. All right, so let's walk through one of these. Kind of talk through it, and then we're going to do a lot of NMRs today. And the more of these we do, the better you're going to get at them. Let's start by just taking a look at this here. All right, we're going to count a number of peaks because that's typically the easiest thing to do. So this first one we already said had 7 peaks, which means it has 6 neighbors. Our second peak here, 2 peaks, 1 neighbor. We can fill in our integrations. So a 1H is going to correlate to a CH. A 6H is going to correlate to 2 CH3s. So we said the thing that's attached to a bromine is going to be in this 3 to 4 range. We can start with that. So we know there's only a CH here. So let's take it. Carbon makes 4 bonds, which means it has 3 open positions if we have a CH. So we said 3 to 4 range, that most likely has this bromine on it. We can put our bromine here. When we did our neighboring hydrogen search, we said that this has 6 neighbors to it. So in order to get 6 neighbors, we would need to put a CH3 on either side. Similarly, these CH3s here, each of them are supposed to have 1 neighbor ring hydrogen. So if I look at this CH3 here, it's next to this hydrogen, that's its 1 neighbor. Same thing over here, this CH3 is next to 1 hydrogen, so that's its neighbor. All right, so we're going to go down and look at the next example, which is fairly similar. We're just dealing with the chlorine again. I'm going to give you guys a little bit of time to try to do this one on your own. We'll talk through it, and then we're just going to keep moving through these today. We'll do, I don't know, probably 15 NMRs, maybe more, to kind of slowly introduce yourself to them. So go through this, write out your integrations, write out your number of peaks, and then I recommend trying to read it from left to right. So starting with that peak that's on the left, it's the furthest one down. It probably has the chlorine, and then trying to figure out neighboring hydrogen pairs that would make sense. So I'm going to give you guys about, let's say, till 9:45 to try to do this one. And then we will go through it together.
I have a question.
Sure.
For the 3H and the 2H that are right next to each other, how do you decipher which peak belongs to which?
Oh yeah, so this is one I probably have to write out for you guys. I can do that right now. So this would be 2 peaks, and this one would be 4 peaks.
Thank you.
Yep. Oh, and the PDF for this is available under modules if anyone wants to. Module, it should be under module 1 if anyone wants to download it, and so they don't have to keep looking at this tiny screen. Okay, so let's get started on this one. I'm going to write out the integrations. We've got a 1H over here, so a CH. 3H should be a CH3. CH2, CH2, CH3 here. It is often best to just kind of read these left to right. So we have a CH. We're going to start with that as our beginning of our molecule. Because it's so far down in this 3 to 4 range, that means it's the most likely to have our chlorine that we can see in our formula on it. So we're going to start by putting this Cl on here. So now we're supposed to have 5 neighbors. So an easy way to add up to 5 would be 3 and 2, which makes sense because we only have CH3s and CH2s left. So if we put one CH3 on one side, I'm going to put it on the right side. It doesn't really matter which one you do. And a CH2 on the left. We can take a look at our CH3s. So this CH3 we just put on here is next to one neighbor, which means it should be a doublet or have 2 peaks. Looking at the 2 CH3s we have one here, one here. This one is 2 peaks, this one's 3 peaks. So that means the one with the 2 peaks is most likely what we have. So because of that, we can kind of just cross this guy out. We've already used it. All right, let's take a look at our CH2 now. So this CH2 here, it currently has one neighbor. We have 2 different options here. We can either have one that has 3 neighbors or one that has 5 neighbors. Currently we have 1 neighbor, which means we would need a CH2 next to this one to give it to 3. To get 5 neighbors, we need a CH4, which doesn't really exist. So this isn't possible. It's going to have to be another CH2 that's next to it in order to get to 3 neighbors. So if we put another one on, I'm going to erase. All right, so that takes care of another CH2. I'm going to cross it out. Oh, that's erase. I'm going to cross it out. We've only got one CH2 left, which means this one has to be that. It's supposed to have 5 neighbors. Currently it has 2, so to get to 5, we have to have 3 more. Giving us this structure. And that CH3 is supposed to have 2 neighbors. It's next to a CH2, so that makes sense. Okay, we are going to do what's called assigning an NMR, which is where we're going to say which peaks correspond to which carbons. So I'm going to label them A, B, C, D, and E here. And we're just kind of going through and saying what we already did. So A is going to correspond to this proton here. B was our first CH3 we put on. C was our first CH2. D was our second CH2. And then E was our last CH3. So this will be a fully assigned NMR. If we were doing an exam, this is what I would expect you guys to be able to do. And again, we're gonna spend the entire day on this, so you'll get used to it the more and more we do it. Okay, are there any questions on this one up to this point? Okay, so we are gonna move on to erase. Let's see. Talking about this bottom one here, I'm going to zoom in a little if I turn. Yeah, okay. Let's talk about this example down here. We're going to start moving on to oxygen examples. So this has one oxygen in it, which is going to make it slightly different than when we were dealing with bromines and chlorines. Most of the principles are going to be exactly the same. Our biggest difference is that oxygen itself can sometimes have a peak, as opposed to a bromine or a chlorine, which never did. So there are 4 different forms that oxygen could take. We could have an alcohol. We could have an ether. We could have a ketone. Or we can have an aldehyde. And we're going to talk about each one of these separately. They all have kind of tells to know which one you have. So the alcohol is going to give us a small broad peak. So on our NMR, we're going to see something that looks like this. Or if we look at the example that's drawn, it's going to be this here. You see this little odd peak. This is a telltale sign that you have an alcohol. Immediately when you see one of these small peaks, you should know there's an alcohol in my sample. It also is going to give us a peak in that same area that we got a halogen in. So this hydrogen here is going to show up in the 3 to 4 range. So this is going to be different than an ether. So our ethers, which we'll talk about again in a minute, and I'm going to save the 2 carbonyls for after we talk about ethers. So we'll do a bunch of NMRs and we'll go back to the carbonyl ones. The difference is that we don't have, for an ether, we don't get this peak, this like broad peak here, and we end up, assuming these are not symmetrical, so we have something like this here. So because we have 2 bonds to oxygen, this peak would show up in the 3 to 4 range. And so would this one. So if you see 2 peaks that are in that 3 to 4 range instead of just our typical 1, that's going to be a big sign that we have an ether instead of an alcohol. So alcohols give us this broad singlet here. Ethers give us 2 peaks. in the 3 to 4 range.
Are they
After that,
small as well?
what'd you say?
Are they small as well?
Nope, they're just normal peaks,
Okay,
like one of these.
okay, thank you.
Yep, you're welcome. One thing to note is that this OH doesn't count as a neighboring hydrogen. Because of hydrogen bonding, you're constantly losing it and it's kind of going on and off. So that one is not going to count when you're doing your H bond counting. Okay, so I'm going to let you guys work through this one. Give it a try and then we'll work through it together. So as we said, this is most likely going to be an alcohol, or it's going to be an alcohol. I mean, it's got that small peak there. Not most likely. And you kind of treat it like it's a bromine when it's on your molecule. So I'll write out some of these peaks. I'm going to give you guys, let's say till 10 to go through them. We'll go through this together and then we'll take a little break and do some more problems. So I'll write out all your peak numbers so you guys can see them. Okay, so we are still reading these kind of left to right. We got a peak that's in this 3 to 4 range here. Oh god. That is most likely going to be attached to our alcohol. We have this broad peak, which shows us that we have an OH. So let's start out by writing. I don't love the green. Red. Our CH, we're going to put our alcohol on it because it's in that really far down range. From here, it's supposed to have 5 neighbors. We said we don't count the OH as 1. So we need to have probably 2 and 3. It's the most logical way. Looking at what we have a CH2 and a CH3. We can put that on either side of this. So I put a CH3 on this side. We can cross this one out. Put a CH2 on the other side. That CH2 is supposed to have 2 neighbors. Currently has 1 from our CH here, so it needs another one, which makes sense because we got a CH here. So putting a CH on the side of it. Okay, our CH is supposed to have 8 neighbors. It currently has 2 from the CH2 next to it, so it needs 6 more, which would correspond to these last 2 CH3s. If we go back and label them A, B, C, D, E, and F here, A is going to be our CH, B is our OH, C will be our other CH that's way down here, D is our CH2, E is our CH3, and F is our 2 symmetrical CH3s. Are there any questions on this NMR? Okay, let's take about a 7-minute break, meet back at 10:10, and we will do some more alcohol-based NMRs. All right, so let's get back to it. I'm gonna skip the top one on the second page. It's honestly just too hard. So let's move on to this one. We still have an alcohol. No, we still have an oxygen. This formula, for some reason, there was a 6 and a 7 on top of each other. I think it should just be a 6 because there's 1, 2, 3, 4, 5, 6 peaks. None of those were the right number. 4, 5, 6 peaks. So I don't know where that 7 came from. So now we're dealing with the other type of situation. We don't have that broad peak anymore. It looks like now we have 2 separate peaks in our 3 to 4 range. Which most likely means that we're dealing with some sort of ether here where we have, taking a look at this, probably CH2 is on either side of our oxygen. So with that in mind, let's say oxygen here. Each one of these would correspond to one of these two sides here. Take, I don't know, let's say till 10, 15 to try to figure out the rest of this. And then we will go through and talk through it together. I'll write out your peaks like I have been to make it a little bit easier to read. All right, so we are dealing, we got 2 CH3s, which, oops, let's go back to red. Means that each have an opening on either side. One of them, the one on the left here, supposed to have 3 neighbors. Currently has 0 because it just has an oxygen there. So putting a CH3 on the side. Should fulfill that. Our other one is supposed to have 1 neighbor. So a CH would make sense there. It should also, it should have 8 neighbors. It currently has 2, which means it needs 6 more. So this 6H, which would be 2 symmetrical CH3s, would give us our final product. Doing some labeling A, B, C, D, E here. A should be our CH2 that has the 3 neighbors, so that would be this side. B would be the one that has the 1 neighbor. C is our CH. D is our CH3. And then E with our 2 symmetrical CH3s in the end. Are there any questions on this one?
I have good questions about oxygen between CH2. So how we know oxygen between CH2 are not CH3? We have another case.
Oh yeah, so it's gonna always be this. You have to look down at this like ppm region at the bottom. So when it's in this far down 3 to 4 range, that's how we know it's attached to the oxygen. So because these ones over here are in this like 0.5 to 2 range, they're not attached to anything besides carbons. When we're all the way down in this far range, this is going to tell us that it's attached to like an oxygen or a halogen or something like that. Does that make sense?
Yes, thank you.
You're welcome. Okay. The next, so this is technically where we're going to stop in terms of this exam. I'm going to go through some other types of NMRs just to kind of give us a crash course to make it a little bit easier when we get to other chapters. So we are going to talk about some different carbonyls and then some aromatic rings. Even though that won't be on this first exam, it'll be a lot easier for you guys to pick it up later down the road if you guys have already done it once. So through this exam, we'll stop at alcohols and ethers, but I'm going to cover a bit more. So this next one is going to be where we start dealing with carbonyls. So when we had our alcohol and our ether, these positions that were bonded to an alcohol always showed up between 3 and 4 ppm. When we deal with carbonyls, it's going to be a little bit different. So there's 2 different carbonyl possibilities. Well, technically 3, but we're going to start with the first 2. And these are going to be a little bit different. So we're not directly bonded. This would be the carbon that's directly bonded to the oxygen. Instead, we're a position away, but because the double bond is so strong, it's still going to shift our carbons or protons. I'll actually erase this guy and read it a little lower. So because of that, this is going to shift these all the way to the, or not, they're still going to shift these down to about the 2 to 3 range. And same thing for this aldehyde, the position that is kind of one away, these get shifted to about 2 to 3. For an aldehyde, because you have a proton that is directly attached to your oxygen, this one's going to be dramatically further. This is going to show up in the 9 to 10 range, and we'll do an example of this in a minute. But that's going to be what separates an aldehyde and a ketone. So this is a ketone, this is our aldehyde. I'm just going to kind of walk through this example here. This is an example of extended symmetry. So up till now, we've only really seen symmetry like this, where these two end positions are going to be symmetrical. You can also have things like if you have a long chain, say we have this molecule here, these two positions are symmetrical, as well as these two positions are symmetrical. They're just much further away from each other, as they would be on an example like this. So they're still going to react similarly, where they're going to give you one signal instead of two. Okay, so like I said, oops, maybe too much. Going to walk through this one. The aldehyde example, I think, is a little bit more straightforward, so I'll have you guys do that one. We have a peak between 2 and 3. Which means we're going to have some sort of carbonyl. It's got 4 peaks, so it should have 3 neighbors. This one has 3 peaks, so it should have 2 neighbors. We have a 4H, and generally the best way to make a 4H is going to be 2 CH2s. Having just like CH4 by itself is terminal, so there's no reason that that would actually show up. And then 2 CH3s for this 6H. So in order to get them in the 2 to 3 range, this is going to be an example where we have a ketone, and each of these CH2s are on either side. In order for this to remain symmetrical, in order to have this 4H here, we would need to have the same thing on either side of these CH2s. So a CH3 in either one of these is going to make sense for that. Assigning our protons, A would be these CH2s here, and then B would be our CH3s. Okay, so that's kind of a crash course. 2 to 3 range means that we're in this adjacent to a carbonyl territory. And then if we have like a 4H, we're starting to see extended symmetry. I'm not going to talk about extended symmetry on this first exam. Just wanted to kind of, again, do like a little bit of an introduction to it. So let's move on past this one. We're going to do an aldehyde example, which is a little bit more straightforward. And I'm going to have you guys do most of that one. So let's see. I'm going to switch to here. Okay, so aldehydes are very easy to recognize. Anytime you have a peak, between 9 and 10, this is a dead giveaway that you have an aldehyde. Just like anytime you have like this small broad peak, this is a dead giveaway you have an alcohol. This is one of those things you just need to memorize when you're doing these. And I'll give you guys kind of a table, or you could write it down on your cheat sheet as to what you actually need for these. But there are like general ranges where you're going to see things. So aldehydes always show up between 9 and 10 ppm. Alcohols always have these broad peaks here. Just little things that let you identify what you're dealing with. So knowing that you have an aldehyde, I want you guys to go through and try to solve the rest of this one. Unlike an alcohol, this does count for hydrogen or number of neighboring hydrogens. So just kind of use your normal rules to get there. I'll write down the integrations, not the integrations, the number of peaks. I'll give you guys till around 10:30 to go through it, and then we'll talk through it together. Okay, so for an example like this, I would tell you what the peaks are because it's so hard to see. I won't necessarily give you like the number underneath it, but I'll at least tell you the number of peaks for it. Like I would write 3 peaks, 3 peaks, 9 peaks, and 2 peaks on this one, just so you don't have to identify them. Or I'd give you something that looks like, it's hard to blow up these. Yeah, I'll give you the number. Ooh, I have to find the spot. I'll give you that kind of information on these ones. Okay. You're not expected to like decipher if there's a space there or not. That shouldn't be the thing you're working on. Because if you do this with an actual program, it's easy to like zoom in and count them. Okay. We said we have an aldehyde. Taking a look at our aldehyde, it's supposed to have 2 neighbors. So it makes sense for that to have a CH2 attached to it. We've got a CH2 right here. So we can put that on our molecule. Our CH2 currently has 1 neighbor. It's supposed to have 2 neighbors, so adding another CH. Oops, I went in red. Would fulfill that. From this point here, our CH is supposed to have 8 neighbors. It currently has the 2, which means it needs 6 more. Giving us this product here. Going through and labeling them. A, B, C, and D here. A will be our aldehyde. B is our CH. Nope. B is our CH2. C is our CH, and then D is our 2 CH3s.
Dr. Bayo, I have a quick question.
Sure.
I'm just trying to conceptualize the numbers up on top. For example, with the 1H, I understand the number on the bottom. That makes a lot of sense. But what exactly does a 9 represent? I'm trying to just wrap my head around that.
What does the 9 represent?
Yeah, you see in C with the 1H. So it's 9 and under it is an H, or sorry, an 8. What does the 9 represent?
Oh, okay. So the 9 is technically you get 1 extra peak for itself. And then 8 is equal to the number of neighboring hydrogens.
Okay.
So for this here, from looking at it, it has a neighbor on this side, a neighbor on this side. And then technically, even though it's a CH2, it's going to read it as 1. That's just how the system works
Okay.
with like the magnets and things like that. So it gives you 3 peaks for it, and you're able to determine your number of neighbors just by taking that 3 and minusing it by 1.
Okay.
That helps?
And this is H. Is this, yes, absolutely. And this is HNMR or is this NMR?
Yes. This is HNMR. There's technically something called carbon NMR, which we're not going to talk about. You might see it in lab.
Okay. All right. I appreciate that.
Yep, you're welcome. All right, let's take a look at the next one. We're going to start moving into some 2 oxygen territory. I don't know what that random 1H floating off there is. So we're going to move into some different functional groups. This one is going to be a carboxylic acid. So we're getting to the point where we're just going to start recognizing things. So between 9 and 10 was an aldehyde. Between 10 and 12, any sort of peak in here is going to immediately correspond to a carboxylic acid. This H here is actually removed from this carbon, so it isn't going to count as a neighbor or anything. From this point, you guys should be able to do the rest of it. So I'm going to give you guys about 2 minutes to try to fill in the rest of this. I'll write in your peaks. If I can figure them out. Geez. 1, 2, 3, 4, 5, 6. So try to fill in the rest or left half, right half of the molecule. Ignore whatever's going on up there. And as kind of a reminder, a peak in this 2 to 3 range is going to be adjacent to your carbonyl. So this will be the next peak that you guys see on your molecule. All right, so we have a carboxylic acid. Our neighbor looks like it is should be in the 2 to 3 range, because if it's next to a carbonyl, that's where it's going to show up. So that means this next peak, this 1H here, is going to be what's attached to our carboxylic acid. It's going to have no neighbors. This carbon doesn't have any hydrogens on it. You have to go to the oxygen before you get to another one. So it needs 5 neighbors. It currently has 0. So that would easily add up, based on what we have left, between 3 and 2. So a CH3 on one side and a CH2 on the other. CH3 is terminal, so we don't have to worry about that. The CH2 is supposed to have 4 neighbors. Currently it has 1, so we need a CH3 on the other side of it. We wanted to label these. A is going to be our OH from our carboxylic acid. I'm not going to circle it. B would be our directly bonded to our carbonyl. C is our CH2. We have 2 different CH3s. One of them should have 1 neighbor. The other one should have 2. So the one that has 1 neighbor should be the one that's on top here, because it's next to this CH, versus this one down here, which is supposed to should have 2 neighbors because it's attached to this CH3 here. Any questions on this one? Okay, we are just going to touch on aromatic rings real quick. I think there was a question on the last one about the formula. I'll give you guys a second to finish writing this, then we can go up and take a look at it. There's a chance I messed up the formula. All right, so let's, oops. Question in the chat. So does the oxygen only have its own peak when it's in? Yes. So yeah, the only reason this oxygen had a peak for an alcohol was because it had that proton on it. Same thing over here, a carboxylic acid has a proton on it. For things like ethers, ketones, they don't have any protons on these oxygens. Same thing over here. So they won't give a peak. Our aldehyde doesn't have a peak on the oxygen, but it has a peak on the carbon that's attached to it. So this guy will give us a peak. Because we're dealing with proton NMRs. If it doesn't have a proton, it's not going to show up as anything. Does that answer your question? Okay. So there was a question about the formula up here. Let's take a look at it. C5H10O. Did I mess that up? So 6, 7, 8, 9, 10. So that's the number of hydrogens. 2, or 6, 8, 9, 10. And there'll be 1, 2, 3, and then these two CH3s will be 4 and 5. So yep, that formula should be fine. Should be C5H10O. Okay, last thing we're going to talk about briefly is aromatic rings. And this is another one where we're just kind of recognizing ranges. So anything that's in this 6.5 to 8 range here is going to be an aromatic ring. And for the sake of this class, it's going to be benzene. You're not going to get much information out of here because there's going to be a ton of peaks on top of each other. The big information you're going to get is right here. And for this little lecture, we're only going to talk about 5 H peaks. So a typical benzene ring would have 6 hydrogens on it because we don't know we only have 5. That gives us kind of one empty space here. Things that are attached to our benzene ring are also going to show up in this 2 to 3 range. So this is directly attached. Is a 3H. So we know that this would be a CH3 here. If we were labeling this A and B, so A would just be all of these hydrogens, and B would be our CH3 here. All right, we're going to do a slightly more complicated one. And call it for the day. So I'm going to give you guys about 4 minutes to try to work through this one. And then we will be done for the day. So, well, I guess 3 minutes now. So 10:58, we'll meet back to talk through this. I'll write out some of our normal peak numbers and things like that. Okay, so big peak between 6.5 and 8. It's got 5 protons on it, which means we have an aromatic ring with 5 things filled into it. We've got a peak between 2 and 3, which means that's our next carbon in our sequence. Because that's so close to our aromatic ring, that's where it's going to show up. So we can put this CH on here. It's supposed to have 5 neighboring hydrogens. Easiest way to make that will be 2 and 3. The CH3 is going to be terminal, which means we only have to focus on the CH2. CH2 is supposed to have 4 neighbors. Currently has 1, so we would need a CH3 to add up to 4. Let's do some assigning. So this was A, nope, not D, B, C, D, and E here. A is going to be the ring. B would be our CH. C is our only CH2. We have 2 different CH3s to discern between. D is supposed to have 1 neighbor, so it makes sense that it would be this top one because it's next to a CH here. And E is supposed to have 2 neighbors, so it would be this bottom one because it's supposed to be next to a CH here. Okay, so that is kind of our NMR crash course. Are there any questions on this? Okay, this is the end of material that's going to be on exam 1. On Monday, we are going to go through all of the practice exams and do kind of a review of everything. So up to this point, this is all the material that we're covering. I will see some of you guys in recitation today. If not, I will see you guys on Monday. So have a great weekend, and I'll see you guys later.
May I see C9H12? Can I practice more?
Oh, you want to see the next one?
Yes.
This might be a concept we haven't covered yet. So yeah, this is when we start getting into multiple. This is actually going to be nope. This here, which we'll talk about. I think this is exam 3 material. That might be exam 2. No, it's exam 3. This is what we'll talk about during exam 3.
Yeah, so that is not in the exam 1, right?
Right. Yep.
It's more complicated, right?
Yep.
Okay, got it. So that's you mentioned the exam 1 will be may include alcohol and ether.
Yep. So yep, alcohols and ethers. Yep.
Not like benzene, aromatic ring like that.
Correct. And not aldehydes, ketones, or carboxylic acids.
Oh, okay, I got it. So I just have quick questions about the reagents. So
Okay.
how about the reactions like AlX4? So that is can make the products is like what?
Was that in one of the homeworks?
Yeah. It's
Okay.
kind of like this. So I just have quick questions about it.
Yeah, that one is not going to be on this exam. If you stop by office hours, I can walk you through the problem, the answer to that one. I should have taken that one out. We're not covering that till exam 3, I think.
So how about I just one more. So how about the reactions R2BH is look
R2BH is the same. That's the same as BH3.
Okay, it's the same BH3. Okay.
Yeah.
And you will otherwise I will stop in your office hour. Thank you so much, Dr. Bell.
You're welcome. Have a good day. See you in an
Yeah,
hour
you
or
too.
two.
Thank you. Yeah, see you.